Hello, this is Mr. Gilmore with the 4.2 Parallel Lines and Transversals lessons. Today we're going to be looking at what the definition of a parallel line is. We'll also take a look at transversals and how they actually will form some new angle relationships for us. Let's start with the definition of parallel lines. By definition, a line is parallel to a coplanar line when they do not intersect at just one point. So you may have actually seen your definition of parallel lines before, such that you will say that they never intersect. However, we are going to add a little bit more to our definition. You'll see why in just a second. And also one thing to consider with parallel lines is that lines do need to be coplanar, because if they're not, there's actually a second form of lines which are called skew lines in space. These are lines that also don't intersect, but they're non-coplanar. We need parallel lines to be coplanar, and we're also going to say they do not intersect at just one point. What does that mean for us? It means, doesn't this imply that a line is parallel to itself? It is. Reflexivity of parallelism is actually a true thing. That a line, in fact, is parallel to itself. Why? Well, is it coplanar? Yes, it's in the same plane. And does it intersect itself at just one point? No. At just one point? No, it does not. Which means it does intersect itself all points, which means it's not just one point. So that does mean it satisfies the definition of parallel lines. So yes, a line that is fact does not intersect itself at just one point, because it intersects itself at more than one point, will then be considered parallel. Now, we're going to use this reflexivity of parallelism to actually help us out in the future proofs of things that we'll see with parallel lines. Now, how we label parallel lines in our figures, we actually use arrows on each pair of parallel line to denote parallelism. For example, if I had a second pair of parallel lines here floating through the space, and I wanted to actually state that these lines were parallel, I could use a double arrow on them. So I could say this is line M, this is line N. I could say that line M is parallel to line N. This little symbol between H and J here, and this little symbol between M and N is the parallel symbol, meaning H is parallel to J, M is parallel to N. And we can actually have multiple sets of parallel lines, and we can denote those parallel lines with the arrows. Now, let's jump into what a transversal is. We're going to actually conclude the lesson today by looking at what a transversal is and what it does for us in terms of angle relationships. So a transversal is where we have a line intersecting another pair of lines at distinct points. In other words, in our diagram below, line T is intersecting line H and J, but not at the same point. We want them to actually intersect at distinct points. So we would call line T a transversal because it's a line that intersects two other lines. I should say, really, two or more other lines would be then considered a transversal. Now, it is a relative matter on which one we would consider to be transversal. In our diagram here, if we consider T the transversal, of course we'd see that yes, T is crossing through H and J. However, T could also not be considered the transversal. We could actually have chosen H to be the transversal, and H then intersects at T and also J. But then we didn't have to let H be the transversal. J could have been the transversal. So depending on our perspective of which line is chosen to be the transversal, then we know which lines are going to be non-transversal lines. So again, our perspective changes. A line could be both transversal and non-transversal, but not at the same time. Now, when we take a line, a transversal, and we intersect it with two lines at distinct points, what happens is there are four angles formed at each intersection. Well, then what we can do is break down those relationships of angles. And this is where we're beginning to look at forming new angle relationships. We've been looking at angle relationships in chapter 1, right? Bring two angles together, give them a name. We found vertical angles. We found linear pairs. We found complementary, supplementary angles. Now we're going to add some more angle relationships in this chapter. So the first thing we want to denote is that there are actually, when we intersect a transversal with two other lines, 8 total angles are formed. And those 8 angles can be put into two different buckets. There's the interior angle bucket and the exterior angles. If we take a look at our diagram, if we think about where M and N are being intersected by line T, there's this interior space between line M and N, which means the angles that are formed on that interior space are known as the interior angles. So angle 3, 4, 5, and 6 are interior. Well, then what are the angles that are not formed in that interior? Well, then those would be called the exterior angles. So we have angles 1, 2, 7, and 8 would be the exteriors. What we're going to do is we're going to begin to relate these interior and exterior angles together and give them some relationship names. Let's start with this first relationship name called the consecutive interior angles. The consecutive interior are the most easy to spot, and here's how. Consecutive interior angles are interior, which, right, it's in the title, consecutive interior, meaning we're only dealing with our angles that are in interior. In this case, we have angles 3, 4, 5, and 6 are interior. So angle 3, 4, 5, and 6, what does it then mean to be consecutive interior? Well, they're interior and they lie on the same side of the transversal. In other words, if I find one on the left, then this other angle pair is also on the left. If I find one on the right, then the other angle pair is on the right. And it depends on the perspective. Maybe it's up and down, diagonal, however we're actually perceiving these angle relationships. In this case, angle 3 and 6, if we take a look, angle 3 and 6 are a pair of consecutive interior. They're interior, and they lie on the same side. Same thing about angle 4 and angle 5. They're interior, and they lie on the same side. Now, as some other interior angle relationships, let's take a look at our next pair. We call this next pair the alternate interior angles. Alternate interior angles are actually, again, interior, but this time we need to specifically state that they are non-adjacent interior. So they're non-adjacent interior. So actually there's two criteria there. They're interior and they're non-adjacent. And the last criteria is that they lie on opposite sides of the transversal. So if I were to actually pick angle 3 to begin with, what would then angle 3's alternate interior angle be? Well, angle 3 is already interior. I need a non-adjacent interior. Well, that means I rule out angle 4. That means I'm left with angle 5 and angle 6, but it has to then be on the opposite side, which means angle 6 is out. So the only pair that angle 3 can be paired up with then is angle 5, and that is a pair of alternate interior. Same story goes for angle 4 and angle 6. That's another pair of alternate interior angles. We can apply this same story to the alternate exterior angles. So you're going to see that the definition between alternate interior and alternate exterior only change by the vocabulary of changing the word interior to exterior. So a pair of alternate exterior angles are again non-adjacent exterior. So now we're choosing from angles 1, 2, 7, and 8, and they have to lie on opposite sides of the transversal. So if I were to again pick, let's say, angle 2, that's my exterior angle there. What would be its alternate exterior? Well, I need an angle on the opposite side, which means it leaves me with angle 1 and angle 8, and it has to be non-adjacent, which means angle 1's out, so angle 8 would then be its pair. So angle 2 and angle 8 are a pair of alternate exterior, and then angle 7 and angle 1 would be a pair of alternate exterior angles. There's one more angle relationship we form, and this one actually has 4 pairs in it. We saw in the last 3 examples there were only 2 pairs. This one actually has 4, and the reason why is because we're going to pair a single exterior angle with a single interior angle. Since there are 4 interior and 4 exterior, that means we form 4 total pairs. So these are called corresponding angles. Corresponding angles are 2 angles in which they are non-adjacent, okay, so they can't be next to each other. One is interior and one is exterior, and they lie on the same side of the transversal. I'm going to pick angle 1 as my example to start out with. Angle 1 is already an exterior angle, which means I'm going to pair it with an interior angle, which leaves me with 3, 4, 5, and 6. Well, it can't be adjacent, which means angle 4 is out. And it has to lie on the same side, which means angle 3 and angle 6 are out. That leaves me then with angle 5. Angle 1 and angle 5 then are a pair of corresponding angles. Another way to think about angle 1 and angle 5 being corresponding, imagine this. Imagine taking these 4 angles here and cutting them out of their intersection, and then sliding that intersection all the way down here so that it would actually lie on top of this other intersection. So if these two then were non-distinct points, they were actually, or if they were, non-distinct points, they were actually the same point. Notice how angle 1 and angle 5 would then essentially overlap. And because they're not exactly overlap, but because they're in the same location, we would consider them corresponding. So the other pairs of corresponding angles, if I were to choose, let's say, angle 3 is interior. Now I need an angle that's exterior, non-adjacent, which means angle 2's out. And it has to be on the same side, which means angle 1 and angle 8 are out. That leaves me with angle 7. So angle 3 and angle 7 are a pair of corresponding. And we can follow along again with the other angle pairs. I have angle 2 and angle 6, and then angle 4 and angle 8 would be pairs of corresponding angles. Let's now use what we've just learned to actually answer a couple questions. Let's take a look at a pair of 2 angles and then name what their angle relationship is and then what their transversal. It actually might be easier to actually answer what the transversal is and then name the angle relationship. Let's take a look at angle 2 and angle 6. I'm going to answer what's the transversal first. The transversal is an easy question to answer, which is, what line does angle 2 and angle 6 have in common? Well, if we take a look, angle 2 is formed by line A and line M, and angle 6 is formed by line A and line N. Notice that line A is the common line, which means what's the transversal? Line A is the transversal. Now I can name what their relationship is. Angle 2 and angle 6 are on the same side. One is interior, one is exterior, and they are non-adjacent, which means they must be corresponding angles. That is their relationship, angle 2 and angle 6. Now, you may be wondering, how did I know angle 2 was actually exterior? Here's an interesting question. Since A is our transversal, that means M and N are the non-transversals. That means this would be the interior. But our perspective can change, can't it? Because what if M was the transversal? That means A and B would be the non-transversals, which means this is the interior. So actually 2 can be either an exterior angle or an interior angle based on the transversal. So it's, again, there's some relative adjectives we can apply to these angles depending on which line is actually the transversal. Let's take a look at another example. Same diagram, but two different angles. Let's pick angle 2 this time and angle 15. Now, let's answer what's their transversal first. Angle 2 and 15 share a line, line M. So M is their transversal. What then is the relationship between angle 2 and angle 15? Angle 2 and angle 15, they lie on opposite sides of that transversal. They're not adjacent, and they're both interior. Remember, because A and B are being cut, which means there's an interior space between those two. So 2 and 15 are alternate interior angles. And there we have it. That's angle 2 and angle 15's relationship. Let's look at 15 and angle 9 this time. Let's answer what's their transversal. That would be line B. They share line B, which means we're looking at M and N being the non-transversals. So again, this is the interior. Well, 15 and 9 then are both interior, and they're on the same side. That means we have consecutive interior angles for this one. Consecutive interior angles. A couple more. Let's look at angles 7 and 11. Angles 7 and 11 share transversal. They share line N. And in this case, if they share line N, that means A and B are the non-transversals. That means the space is here. Well, the 7 and 11 angles then are not interior. They have to be exterior. They lie on opposite sides, which means these are alternate exterior angles. Let's take a look at a last example here with angles 8 and 15. 8 and 15. The question I want to ask first is, what is their transversal? Well, if we take a look, 8 is built using line N and M, and 15 is built using line M and B. That means they don't have a line in common. And because they don't have a line in common, that automatically means there is no relationship. There is not an angle relationship between these two angles because they do not have a transversal. There isn't one. And in order to form those relationships we just looked at, those four new angle pairs, we have to have a transversal in common. So here's a question to you. Let's bring angle 12 into the mix. Angle 8 and angle 12, what's their relationship? Those are corresponding. Look at angle 12 and angle 15 then. What's their relationship? They're also corresponding. So here's a little brain buster for you. Is there such thing as transitivity of corresponding? That if 8 is corresponding to 12 and 12 is corresponding to 15, does that make 8 and 15 corresponding? No. There's no such thing as transitivity of corresponding. We have learned that transitivity does apply with certain relationships. It applies with relationships of equality and relationships of congruence, but it doesn't apply to every single relationship. We're going to see in this chapter that it does apply to parallelism. When we talk in terms of lines, that if A is parallel to B and B is parallel to C, we can prove that A and C are parallel, which means proving that transitivity of parallelism is a thing. But transitivity corresponding, no, not a relationship that actually holds true. Because do 8 and 15 have a transversal in common? No, which means they cannot be corresponding to each other. This concludes our 4.2 lesson on parallel lines and transversals. If you do have any questions, do not hesitate to email me. With that, be good and do good.